All right, so this video will deal with the mean value theorem examples for section 3.2, and these are the last three examples for the section. The mean value theorem, recall, states that you have two conditions if the function is continuous on a closed interval, a,b, and then it's differentiable on the open interval. Differentiable again means that its derivative exists on the entire interval. Then there exists a number c in that open interval AB such that f prime of c equals f of b minus f of a divided by b minus a. And so the derivative at the value c is equal to this fraction. And recall that f prime of c can be thought of as the slope of the tangent line at c. And then f of b minus f of a divided by b minus a, that's just the formula for slope. But in this case, we're dealing with the secant line that goes through the endpoints of the interval. All right, so that's the theorem. And we're going to apply it to these three examples. I've already done 39 in the part 1, but I figured I'd go ahead and redo it. So I've done this in a previous video, but I'll go ahead and do it. All right, so number 39. All right, so we need to check two conditions. We need to check, is it continuous on the closed interval, and is it differentiable? And 6x cubed, this is a polynomial. So f of x is a polynomial. And recall, polynomials are continuous and differentiable everywhere. So I'll put CONT for continuous and DIFF for differentiable. So continuous and differentiable everywhere. So since they happens to be everywhere, then any interval, it's going to be continuous and differentiable. So the first condition, f of x equals 6x cubed, is continuous on closed interval 1, 2. And then differentiable on the open interval. All right, so those two conditions hold. So now I can apply mean value theorem. And I abbreviate mean value theorem as NPT. So what we need, we want to find C such that f prime of C is equal to f of B minus f of A divided by B minus A. All right, that's what we want, and I'll write the function over again with 6x cubed. And we're dealing with the interval 1 to 2. All right, so what I do first is I'm going to actually find the right-hand side. What is f of b minus f of a divided by b minus a? So f of a, in this case, a is 1 and b is 2. So that's going to be f of 1 and then f of 2. Okay, so f of 1, that's going to be 6 times 1 cubed, which is going to be 6. And then f of 2, 6 times 2 cubed. 2 cubed is 8, so that's 6 times 8, which is 48. So f of b minus f of a, that's going to be f of 2 minus f of 1. And then over b minus a, that's 2 minus 1. So that's going to equal 48 minus 6 divided by 1, since because of 2 minus 1. All right, so 42. All right, so that is the right-hand side. So I need to find C such that f prime of C equals 42. All right, so to find f prime of C, I need to find the derivative. So for f of x, it's 6x cubed. Its derivative, f prime of x by power rule, so it's going to be equal to 6 times 3x squared because of the power rule applying to the x cubed. So that's 18x squared. All right, so the derivative is 18x squared. So I set f prime of x equal to 42 and then solve for x. And this will give me the value c. So I have 18x squared equal to 42. I divide both sides by 18. So you have x squared equal to 42 over 18. And then you can reduce that to 21 over 9. So x squared equals 21/9. To get rid of the square, I square root both sides. So that's going to give me x equal to, and then we have the square root of 21 over 9, but when you take the square root of both sides to undoing the square, you consider both plus and minus square root of 21 over 9. And we know the square root of 9 is 3, so this will be plus or minus the square root of 21 divided by 3. All right, now I've got to keep in mind what is our interval. So we need to check to see if these values lie inside the interval. And the interval is 1 to 2, but we do the open interval for C. So only the positives 1, so only square root of 21 over 3 lies in that interval. All right, so C is equal to square root of 21 over 3. All right, and that's how we apply the mean value theorem. All right, so the next example, number 41. All right, so this is the example. Notice this is also a polynomial. So f of x is a polynomial. Polynomials are continuous and differentiable everywhere. So it's continuous on the closed interval, -1 to 0, and then differentiable on the open interval. All right, so the two conditions are met. Now we just got to apply the mean value theorem. So we need to find C such that f prime of C equals f of B minus f of A over B minus A. All right, and A and B in this case are -1 and 0. All right, so our function is x cubed plus 2x plus 4. And f of b, in this case, b is 0, so f of 0. When you plug in 0, you're going to get 4, right? So everything that has an x goes away since it's going to be 0. All right, so f of 0 is 4. Now plugging in -1. -1 to the 4th power is +1. So that's going to be 1. And then -2 plus 4. So 3. Or yeah. Sorry, I got tripped up here. I put a 4 power right here, so that's why I was kind of like wondering what's going on. So this needs to be cubed because there's a cube for x cubed. So then this actually makes this -1 -2 plus 4. So that's -3 plus 4, so that's equal to 1. All right, so that was a mistake. I should have put cube versus to the 4th power. All right, so we have 4 and 1. So basically this portion right here, that's going to be, so we need f of 0 minus f of -1 divided by 0 minus -1. That's what just plugging in what b and a are. F of 0 is 4. And then f of -1, that was 1. And then here we have a 0 minus a -1. That's really 0 plus 1, which is 1. All right, so 3. 3 is what that whole thing is. So we need to find c such that its derivative is equal to 3. All right, and our function's x cubed plus 2x plus 4. So for its derivative, f prime of x, that's going to equal the derivative of x cubed is 3x squared. Derivative of 2x, that'll be plus 2 times 1. Derivative of 4 is 0 because that's a constant. So the derivative is 3x squared plus 2. All right, so then we set that equal to 3. So set the derivative equal to 3. And then solve for x. So 3x squared plus 2 equal to 3. If I subtract 2 from both sides, that's going to give me 3x squared equal to 1 as the result. And then I divide both sides by 3. So that's going to give me x squared equal to 1/3. And then I square root both sides. So that's going to give me x is equal to, and it's going to be plus or minus the square root of 1/3. And you could write this in a, so that there's no square root of 3 in the denominator. So you could say this is plus or minus the square root of 3 over 3 if you wanted to rationalize. All right, so I accept either 1 square root of 1/3 or the square root of 3 over 3. Now we need to check our interval. So our interval So we don't consider the endpoints when we're dealing with C. It's going to be -1, 0 with parentheses. And the only one that lies inside of that interval is the -√3/3, or -1/3. So only C equals -√1/3, or writing it as C equal to -√3/3, lies inside the interval. All right, so that's that example. This next one's number 43. It's going to be the last example. Okay, so our closed interval is -3 to 3. And now note that I can't divide by 1 here. So note x can't be 1 because you'll get 0 on the denominator. Right, so that's undefined at 1. So it's not continuous at 1, which means it's not continuous on the entire interval -3 to 3, which means I cannot apply mean value theorem. So there's discontinuity. At x equals 1. And this is in the interval -3 to 3. Therefore, f of x is not continuous on the entire interval. So we can't apply mean value theorem. All right, and that's it for that one. All right, so this is it for section 3.2.